Hello, everyone. Today I would like to present a sort of recap for some papers that I have read from the previous month of November in the topic of physics, which is very broad, as you will see, and kind of go over why I find them interesting and what we can learn from them, right? So, how this will go, I have selected three journal papers and two from arXiv, and I'm going to force you to listen to me talk about them because I think they're cool. All of them are open access because I am one broke creature, so you can read them yourself if you, for some reason, want to. I'm not going through this alone. You have to read them now. I don't make the rules. So the DOIs and all links related to the explanations are going to be in the description. Huge disclaimer, I can be wrong. Don't take me too seriously. I'm not a physicist and only have a basic understanding of the maths behind all these papers. So please do your own research and don't be mean to me in the comments, but feel free to correct me if I'm getting something wrong or if you have a better understanding of some of this. I would say don't try this at home, but I don't think you could logistically do so. So do what you want. I'm not your mom. Don't create quark gluon plasma or a neutron star at home. I'm not responsible for any damage caused if you somehow manage that. Okay? Okay. So for each paper, I have asked myself the following questions to better summarize them. So firstly, what is this paper about? To kind of give an abstract of what I personally took away from the paper. Summarize any key educational points required to further understand the contents and explain the more important graphs and figures in the paper and how they relate to its point, right? There will also be some further questions, right? Like, why did I choose this paper for this video, right? Because there's a lot of papers that were published in November. I had to narrow it down somehow. And what does this paper change within its field and beyond, as well as what are the further questions that I have about the material and what further research can be conducted in the direction of the paper, because I, of course, had a limited time to allocate to each paper. So this is kind of me admitting what else I want to learn, maybe if I sort of had more time or in general later, right? So let's get into it. The first paper is The Physics of the Gluon Mass Gap by Ferreira, Papavassilou, Pawlowski, and Wink. I should have probably learned their last names before I started recording. Okay, so let's get into it. Let me just pull up. So this paper investigates the gluon mass gap and how that affects the temperatures at which deconfinement occurs. It also fits mathematically something called the gluon propagator, which I assume can just be thought of as what stuff interacts with other stuff and at what lengths, right? Since there's gauges involved, this gluon propagator cannot be measured directly, and maybe it's not because of the gauges. So instead, they measure the deconfinement in different momentum regimes. Now, this paper will bring up ultraviolet and infrared. These are a little bit adapted from our understanding of that, but it's still kind of just like about speeds and energies and wavelengths and all that. I'll explain it if it comes up, which is the phenomenon, right? Deconfinement is the phenomenon when color attraction drops greatly above a certain temperature, which to me is confusing because temperature is usually defined in terms of kinetic energy, but if we're restricting the momentum regimes, then what gives? But maybe I also just have an incorrect understanding of one of the two concepts above. It's possible the momentum regimes are more inherent properties than kinetic energy, such as spin, or it's possible they different kinds of movements. I genuinely don't know. It also investigates the effect of the pion decay coefficient, which shows how deep the chiral symmetry breaking in pion decays is. It's like the one mathematical thing I know about this. So it's like um, in Lagrangian dynamics, when we have a symmetry breaking, it's like at high energies, we have this kind of graph. And then at lower energies, we start to have this kind of U-shaped graph for spontaneous symmetry breaking. And then, right, this, hold on, let me choose a different color. So like something which was this at a higher energy, right, is going to be in this unstable maximum and is going to roll down either here or here. That's how I learned about spontaneous symmetry breaking. All right. But basically, where was I? This paper shows that the pion decay coefficient is insensitive to the gluon propagator in the infrared regime, which I assume to mean strong force no longer acts or acts the same as in the other massive ones, right? So let's move on to the key points. Okay, so lots of stuff here. So what we learned is the gluon mass gap, first of all, is gluons gaining mass even though at the surface level you wouldn't expect them to in the theory, and this is governed by the Schwinger mechanism. Uh, what you will get when you search up Schwinger mechanism online is related, but a different phenomenon in quantum chromodynamics. But the 20th reference in this paper, which I have linked in the description, is 100 pages long and should answer everything you'd want to know. Hopefully. I have not read it in full because, again, time constraints. The results I got with a cursory search were about the QED, quantum electrodynamics phenomenon, in which electron-positron pairs are spontaneously generated when an electric field is applied. The Schwinger mechanism says that even if the theory itself doesn't predict that a boson should have mass, it can still acquire mass through this vacuum polarization function. Basically, if you dry the wets and wet the dries, if you think of it in context of the electric field and turn the field to zero, you could get mass, I think. As also as mentioned in the 20th reference, this mass depends on gluon-gluon interactions, which I presume can be connected to the concept of self-energy or energy that comes from interactions with other particles of the same type. The reason I believe this has something to do with it is because self-energy is also talked about in the vacuum polarization article on Wikipedia. So that's that. The gluon propagator is tricky. It seems to be a little too advanced for there to be any like intuitive explanations online that I can find. But to summarize, what I do understand is related related to how the gluon interaction strength varies with distance, right? Between the quarks, I presume, since the thing with bosons is they're just kind of there. Like you don't need to shoot a gluon at a set of quarks for them to become, say, a proton. They just kind of do that by themselves at the right conditions, whatever those may be. And the gluon propagator describes these conditions and the overall dynamics when these quarks are coupled. Right? So this paper also compares Yang-Mills theory and quantum chromodynamics a lot, specifically 2+1 flavor QCD, right? Meaning there's two light quark flavors, so up and down, and then one heavier quark flavor, which from what I was able to find, appears to be strange quarks most of the time, right? So the difference between these two is that Yang-Mills is more general and also wasn't originally quantized. I would think that in this paper they are using the quantized Yang-Mills theory, but feel free to fact check me on that. And whereas QCD is built specifically for strong interactions, as discussed here. Um, as for the Schwinger-Dyson equation, and I am going to show you what I mean here in the paper. I hope it's showing up. This looks pretty cool. I don't fully understand what that means. It's some kind of adapted Feynman diagram, I think. but I have linked a resource in the description which goes through a little bit of like what this stuff means. I'm not sure if it's like 100% relevant, but I was able to lean a little bit from it, right? It also talks about these like ghost gluon terms. It's not in my script. I'm going off script here, but I think it's like particles that only arise or only start having effects when there's like these kind of loops at like perturbation scales. I'm not sure what I'm talking about. All right, let's do this. And I think that would be all for the key points. So let's move on to the graphs. Figure 7. I spent an embarrassing amount of time trying to interpret this one, honestly. But like roughly speaking, they're saying that beyond some critical temperature, the stable minima become unstable maxima. This is also shown in the figure 2 graph. Hold on, let me switch to it. Right, this is also shown. I um, it was supposed to be shown in this graph. I'm not sure what I was thinking when I wrote this script. This was a really long time ago. I apologize. But yeah, as you can see here, um, these stable minima, let me annotate. Right, these stable minima right here, they become unstable maxima and vice versa. Okay. And which means the confinement occurs, which is when quark gluon plasma or a state where quarks aren't confined into hadrons such as protons and neutrons uh, occurs, right? The axes, from what I can tell, and there's like so much complicated group theory involved. Look up Polakoff loops because I'm not going through this alone, as I mentioned. Yeah, from what I can tell, the axes are somehow related to the eigenvalues of the field, which, from my limited understanding of quantum mechanics, that's like physical states that then go on to form superpositions. Um, and I've also just like realized this while writing the script, but since there's 3 quarks and 8 gluons, I think that might mean that phi 3 is related to how the quarks interact, while phi 8 is how the gluons interact, which actually makes sense since they're called field components earlier in the paper. I assume this is an abstract way to say coordinates or something in terms of which the system is defined. So like for some particular combination of what the quarks and gluons are doing, the quarks might either be free to move around or the gluons would catch them and make them interact with each other. This is also what happens when I'm asked to participate in a social gathering. Again, a lot of complicated mathematics that I still want to learn, but isn't all that necessary to understand why this research is so cool. And really, I just wanted to show off this plot because it's visually the most interesting in this entire paper. And whale chambers have something to do with symmetry. I think it's pronounced whale. Should have looked this up. All right, let's do this. The next graph is, I would say, arguably the most important one. Um, yeah, it's basically just proves the paper's whole point, that when the gluon propagator is changed a little bit in the theory, that change does not affect the critical temperature and the pion decay constant at the infrared scale. And this is because at that scale, something called the gluon dressing function appears in the equations for these parameters, which isn't significantly changed even when the gluon propagator itself is changed. That's what's at the heart of this research. I know I'm not explaining a lot of why this is the case, and that's because the explanation would involve math I don't understand. That being said, it appears to be related to a phenomenon where when the gluons get close to the quarks, their interactions actually get weaker. see the Wikipedia article on asymptotic freedom and its sources, which are also linked. I hope I don't forget to link them. Somebody call me out in the comments if I forget to link them, chat. All right. So there's also like what's shown in figure 10, right? The quark gluon functions, quark mass functions are related to the gluon propagator as well because, and this is something that was surprising for me to learn actually, but yes, quark masses do depend on a variety of factors and the kinds of interactions they're in, or at least appear to. Pretty cool stuff. Did not know that before this paper. So final questions, and this is something I'm going to be doing for each paper. Why did I choose this paper? So I'll be honest with you, I thought this was a different paper at first. I thought it was about the eta prime meson mass gap until after the sunk cost fallacy sunk in. Pun absolutely intended. So I don't know, do with that what you will. Also, the graphs are pretty, okay? Like they are. So what does this research change? Firstly, now we have a better model for the gluon propagator. This is of intrinsic interest to me, but it also provides the foundation to presumably calculate more accurately other important constants of the theory, which could later be verified experimentally, should even be verified experimentally, of course. It also basically fixes a gauge for future works to work with, I think. I mean, it's pretty neat either way. Also, since deconfinement is related to quark gluon plasma, which is still an active area of study as researchers work to predict its physical properties, this paper is just another step towards achieving that, which is pretty cool because this is one of the most like intense, for lack of a better word, state of matter, and it's really interesting, or like extreme maybe, state of matter. So knowing its properties could help identify quark stars, let's say, and truly like the applications are endless here. What are the further questions I have and further research questions that could be had? Well, first of all, it makes me ask how many other like gauge theories would not necessarily require, but would benefit from this kind of research and what that means for the larger mathematical framework of gauge theories. If some of them can then become observables, right? Like the gauges or something related to the gauges or directly depend on the gauges. Of course, it's not the actual gauge we're measuring, but something that depends on it. Once again, that being the mass gap. But this might be something I look into further myself, right? On my own time. Additionally, and this is more mine than the paper's fault, but now I want to reinvestigate the eta meson mass gap. That still seems pretty interesting. I might link some resources to it in the description. It's cool, okay? Um, Second paper on dark matter detection with neutrino observatories. Okay? So this paper proposes a new way to search for dark matter using existing detectors, specifically highlighting the Juno Observatory in Jiangmen, China, which is a multi-purpose observatory and also the largest spherical observatory in the world. Fun fact. It tackles the challenge of detecting sub-GeV, or sub-giga-electron-volt dark matter, which is relatively light, by basically saying, what if more detection per detection? Somebody please get that reference. I'm referencing the more milk per milk post. Specifically, the proposal is to consider these detections at a much larger scale than has ever previously been not necessarily considered, but done, I would say, in order to increase the likelihood that mega electron volt range dark matter leaves a trace on the photomultiplier tubes. The paper calculates the theoretical rate at which sub-GeV dark matter should trigger the detector sensors, as well as proposing a way to clean any data received from future experiments of yearly trends and background noise, effectively creating a framework upon which further searches for dark matter could be conducted. Of course, As stated in the paper, it's better to have multiple results from various observatories corroborate the findings. The reason Juno is singled out is because of the unique combination of size and the chemical used within, which I will discuss promptly. Um, yeah, so the experimental detection setup, like the overall theme that we're going to be analyzing. Um, So the core of the detection relies on so-called photomultiplier tubes or PMTs. Think of these as a pipe through which incident particles can bounce a bunch of times and then show us more light than just the singular potential dark matter particle would have, right? Or would trigger in the chemical in the linear alkyl benzene. This process is known as secondary emission. So to have a photon to multiply, however, the dark matter particle first excites an electron in an atom of the chemical within Juno, and then the electron emits a photon when it goes back to a de-excited state. Right? This is basically just chemistry in a way. So this chemical that we're talking about is called linear alkyl benzene, or LAB. Technically, this is a class of chemicals, but this isn't talked about beyond a brief mention of the structure, which has the formula, and I sincerely hope I do not butcher this. C5H6. Come on. I wrote it down. Come on, I wrote it down. Oh yeah. CnH2n plus 1. That's linear alkyl benzene. So, because of this process of the electrons being excited by incoming potential dark matter particles, um, LAB will frequently be referred to as a scintillator, something which luminesces under radiation due to its chemical properties. As described in the paper, the reason LAB is chosen is because of the structure of the chemical bonds, which basically leave the electrons within the LAB molecules free to go wherever within the particle they are effectively delocalized. Let me just remove this real quick. Within the calculations in this paper, LAB is treated like regular old benzene, presumably to compare with previous results, which also use this, perhaps assumption would be the right word, but in earlier papers, the detectors did actually use benzene, so yeah. These calculations also take into account something called the dark rate of the detector, which is a needlessly confusing name given it's basically the equivalent of background radiation for this scenario. The photomultiplier tubes interact with the LAB to produce some background level of luminescence against which any detections would have to be compared. In addition to this, the research takes into account the importance or highlights the importance of taking into account yearly variations in the detection rates, which vary with a lot of things. Okay, so that's basically the experimental setup. Um, this paper rests completely on this figure, so I'm going to try to do it justice. Let's do this. Um, First, let's go over the left side, and then I will discuss the difference between the two panels. Since what is shown on the right is basically analogous, the axes are dark matter electron cross-section and dark matter energy. To some extent, I feel like that cross-section name is a bit misleading, though I'm sure it does have geometrical significance as it is linked to the probability. that a certain event will occur given a target and an incident particle. Specifically, the larger the cross-section, the harder the dark matter particle will be to detect, as also stated at the beginning of the paper. I would presume the intuition for this is if there's a very large space that the dark matter particle could be found in, the probability it's actually going to be in the space where it hits the electron is much smaller. Fact check me on that, please. The important thing to note with these graphs are the minima. For various detectors as well, again, focusing on Juno because it's so state of the art. Since these represent the masses of dark matter, which the detectors would be most well equipped to, well, detect. As a side note, I'm not sure what the 95% CL means, but it seems to just be some kind of standard press for precision, often noted in dark matter detection related works. So I'm just going to leave it be. Physicists have their conventions, and I'm just gonna let them have this because they don't have a lot. The other things shown on these graphs are the theory benchmarks, which appears to be the predicted values for what kind of cross sections would be possible or likely for different particle models, and the direct detection areas are parameters for which methods of dark matter detection, which are also being used for GeV scale dark matter, would also work. So let's move on to the right panel then. At first, you may wonder how, or rather why, these graphs are so different. After reading the fine print, however, um, come on, yeah, that's, okay, can you lock in? Um, yeah, this fine print right here. Heavy mediator versus light mediator. The difference is that on the left, they're using a heavy mediator, whereas the one on the right has a light mediator. It's not entirely clear to me what the mediator is. Perhaps it's the LAB itself, but its effect is nonetheless important to discuss. So the weight, I would say, of the mediator influences a parameter which describes the amplitude of the scattering, um, which then depends on the momentum of the dark matter particle. What the amplitude is basically the overlap between the incoming dark matter particle and outgoing photon waves. Though this is vastly oversimplified and just my own understanding. On the right, we have a dependence of the inverse of the square, meaning if the momentum is very large, we probably won't be able to see very much. And I've mostly been able to confirm that my understanding is correct because after some mathematical hoops, literally just being a substitution, let me try to find it right here. Pause to read if you need to, with this entire column. Yeah, literally just a substitution. I'm trying to sound fancy because I know uni admissions people might watch this. Let me have it, please. The rate of reaction is directly proportional to this amplitude, right? This M free, weird cursive M, I don't know. Yeah. So, and of course, note the difference in axes. Always important to note the difference in axes. Here it goes to 10 to the negative 39. Here it goes to 10 to the negative 38. Here it goes to 100. Here it goes to 1,000. And finally, while the left and right have this mathematical difference, this doesn't affect the shape of the graph much, right? Of the Juno little parabola, or not parabola, but yeah, like this graph, it doesn't really affect that much. Just like where it's positioned. Okay, cool. That's it. Um, just remove everything for move on. Okay, final questions. Why did I choose this research? Well, it's really as simple as I wanted to highlight dark matter research within this video because it's one of those things that adds the forefront of what I'd say informed public uh, thinks when physics research is mentioned. And specifically, what caught my eye about this research is it's very concrete and creates a relatively straightforward path to starting the kind of search proposed in it. So I'm hopeful that in the near future, at the time scale described here, of course, is like 1 to 3 years, it's saying we will get some kind of news. Okay, what does this paper change? Well, it literally proposes an experiment, a plan for an experiment, which, if it gets picked up, could either one day detect dark matter or point us in another direction with the search. Of course, dark matter is one of those things that nobody really understands, so it's impossible to say that, like, yes, this paper has definitely given us a way to find dark matter, but sub-GeV dark matter seems to be a promising area of research, and in general, the more avenues that are explored, the better, right? Of course, if this experiment is picked up, it's stated that it'll take a few years for enough data to be collected to reach any definitive conclusions. Juno is very much a state-of-the-art observatory. It only began operations this year, and it has a promising future on its own. So I have linked to the web page showcasing the research conducted there in the description as well. Further research questions. This paper pretty clearly lays out what needs to be done in the future. It is first and foremost a proposal for an experiment and to do data analysis. It is stated in the paper that Juno would likely not need any hardware modifications for this dark matter detection analysis to be possible. If only they released the data from their experiments publicly, and I could say a lot of things on the topic of data availability, but won't for sake of brevity because this is shaping up to be a really long video. Yeah, it's also stated in the paper that more precise calculations for the expected detection rate will be performed in future research, accounting for the actual structure of the chemical within the Juno detector, the LAB, right? And in addition to this, future work adapting this method to tailor it to other detectors and combining various of these methods could be done, right? All in all, this is research you will probably see, like this kind of series, maybe, hopefully you will see in future videos like this. Okay. This is like pesky dot. Oh, okay. All right. Paper 3 on neutron star crystallization. Role of symmetry energy at subnuclear densities in proto-neutron star crusts. And I just realized that I didn't read the previous paper's title. I am so sorry. Yeah. So this paper analyzes how the crystallization temperature and time for a solid crust to form on a neutron star. That's not grammatically correct. Yeah, it analyzes how that varies with various parameters. The crust is discussed specifically since it's the first to cool down, basically because it's only warmed from like 5 of the 6 directions adjacent on the surface and the layer directly underneath. Whereas within the star, it gets warmed from every direction, but you understand this. I don't need to repeat why the crust is the coldest part. Come on. Um, yeah, while this may seem obvious, the paper touches on this specifically in the context of neutrino emission and the neutrinos being trapped within the star by proton-neutrino interactions. And it also discusses the parameters for which these interactions occur more often. For example, temperature. The other key parameters are the symmetry energy, which is the difference of energy between if the matter had an equal number of protons and neutrons, and if it was purely neutrons. And this should be easy to imagine since protons repel each other, so there should logically be more potential energy when those protons are present, right? We learned this in chemistry class. Come on, let's lock in. And specifically, the paper shows that the time it takes for a crust to form does not depend on this energy for densities too greater than the representative nucleus. So it's like some kind of heavy nucleus that the cells, for lack of a better term, in the neutron star kind of form around, right? It's like the biggest chunks in the soup of the neutron star. What am I saying? So yeah, trust me, I was confused by this too, but I'm pretty sure it has something to do with how the protons and neutrons are packed together. Um, Another parameter called L considered is the density slope of the symmetry energies. Symmetry energy. It is said that for smaller slopes, the density will be greater, which I interpreted as, all right, time to whip out this again, which I basically interpreted as like this. Uh, this is the symmetry energy as and this is density. I think these might have to be switched around. Okay, yeah, these do have to be switched around. Hold on. I'm just a girl, honestly. I'm just a girl. Let me have those as the woman in STEM. Woman in STEM chat. Okay. It's basically like hold on. I'm sure it as this. The smaller the slope, right? This is like a small slope. This is a big slope. Really, really big slope. Like this, the smaller the slope, the higher the system has access, quote unquote, to larger densities if the slope is smaller. So this paper analyzes various equations of state as well, which are basically equations that allow us to predict the temperature, pressure, density, etc. Thermodynamic stuff, effectively. And it shows that the reason that cooling is much faster with lower L parameters, again, access to higher densities, is because it affects the crystallization temperature rather than affecting the cooling process itself. Cool. That was the abstract. So I believe this paper to be very self-contained in its presentation and the graphs, and I think I will simply explain any key points as they come up, so there's not a dedicated section for this here. All right, let's do this. Figure 2. There's two graphs, like mainly in this paper that I want to highlight. So this one describes the relationship between the mass and radius of a neutron star. And the interesting thing is that the same radius, right, same radius, 11 kilometers, can correspond to two different masses, right, around like 0.4 solar masses and like 2.1 solar masses, I would say. Yeah. So this is because at a certain point, around 2.2 solar masses for the red line right here, right? Like this point right here. The mass becomes so great that there's a new, more optimal configuration for the particles to fall into. This also seems to be why the same mass can correspond to two different radii if for whatever reason, like the old configuration stays, right? Like same mass, different radii, as you can see right here. Um, Yeah, although I don't think I'm like 100% correct in this reading, considering that even after one mass stops corresponding to multiple radii, there's still a slight increase in radius as mass gets lower before like this first inflection point. This is where like the graph becomes vertical. And then between the two inflection points, here and here, um, like this is the most intuitive part of the graph to me because smaller mass corresponds to smaller radius. And after the second inflection point, as the mass gets smaller, the radius blows up presumably to infinity. I think this is because the neutron star can no longer hold itself together and just becomes a cloud of particles, basically. Yeah. No, I did not realize there was an option to clear all drawings. That's cool. Yeah, so as for the other graphs, which vary with symmetry at okay, what is the okay. Yeah, that's it. Yeah, all right. So as for like these two graphs for the models of EOSE and EOSZ, those are the equations of state. And yeah, yeah, they vary the symmetry energy at 2 times density. So like the symmetry energy at some of the densest parts of the neutron star, we can see that for lower symmetry energies, the distance between the two inflection points is lower. Um, these numbers right here, 40, 45, 50, 55, 60, those are the differences in symmetry energies, right? And seemingly E40 does not even have like this interval between the two inflection points at all. Like it's not protruding outwards, let's say. Yeah. So while I do not have an explanation for why this might be, it is an interesting observation with great physical significance, that being the more the protons repel each other and hence are more tightly packed in some of the densest regions of the neutron star, the larger the maximum radius for the star while varying mass will be. Particularly, this radius is found at around 1.6 solar masses. For the E equation of state, right? Like around here, right? Largest radius. Um, and at around 1.5-ish, there's a little bit more variability. Like this is a 1.7. This is closer to the 1.5 number. I can't exactly tell with the 35 one, but I think it's here. Don't quote me on that. Yeah. So the second graph that I want to bring attention to, let me just remove everything. Um, is this one. The time evolution of the temperature profiles for like these two selected models. I consider this the backbone of the entire paper. It's figure 6. The reason is, like these two graphs are, the reason these two graphs are so important is because they show the contrast between the two models and how the L parameter affects the neutron star's formation, right? L parameter is cited right here. Okay, and this is a pretty big difference from what I can tell, right? Um, Yeah. Which, as much as in the paper summary, it really doesn't. Not a lot, at least. Like, instead, it most starkly affects the crystallization temperature. As you can see, despite being measured at different times, these two graphs have like roughly the same shape, with the only difference being like these solid lines, which corresponds to the crystallization temperature as defined in equation 12. Um, yeah. Um, yeah, they have a sharp spike near 10 to the 14th grams per centimeter cube in the H30 model graph, which corresponds to a value of 7.6 megaelectron volts for our L parameter. This basically outright, or perhaps further, I'm not quite familiar with the current state of the research, confirms that the lower the L value, the sooner the crust will form. Similar graphs are shown for representative models in Figure 7, showing what happens at a specific time on the left, and what happens when the temperature of a core is at a specific value on the right, as you can see. Pause if you need to look at it a little bit. So further questions. Why this paper? I think nuclear physics is really cool and interesting, and I'm also curious about how chemistry and physics intersect, since I'm also studying chemistry for A levels right now. And this paper, and I've heard like nuclear physics generalizes some chemistry concepts, and I've not read a lot of nuclear physics papers before, so I was curious how that really works out. The field that I'm personally, like one of the fields that I'm personally trying to go into is quantum chemistry in the future. So yeah. Also, I guess this episode is kind of like states of matter themed now, so whatever. What does this change? Well, there's a lot to hook onto with this paper. Firstly, the parts that touch upon neutrinos are super interesting. I know I've not like talked a lot about them, but they do exist in terms of like what um in terms of like detection, I guess. Yeah, and how the neutrinos are emitted within the process. It's not like super elaborated upon, but it is there, and I do encourage you to like seek it out and read a little bit more about that yourself. Um, yeah, I mean, it might be applicable, but I'm not sure like how applicable it would be in practice to look at these neutrinos to detect neutron stars, considering like how small the time scales are, like as you saw, 118 seconds. But yeah, it might potentially aid in detecting new neutron stars. My hunch is basically that if we start detecting a bunch of neutrinos from a specific direction, accounting for whichever parameters need to be accounted for, I don't know, redshift maybe, with some specific energies, we could say that there's a neutron star somewhere in that direction, if that's not already being done, which is super cool. Also, understanding the cooling of neutron stars could help us probe the history of the universe, so that we have a better understanding of the whole process of a star being born to going supernova to, in this case, collapsing into a neutron star. And of course, in the end, it always leads back to new physics. If we manage to find some kind of experimental anomaly or like observational anomaly, I guess, again, don't create neutron stars at home, please. I'm not responsible for that. That doesn't fully align with our theory, then that's an opportunity to make our theory better. Just like in general, I find the intersection of macroscopic, like cosmology, say, and astronomy, and like microscopic, like particle physics, super interesting, and I'm glad this intersection can bring us closer to understanding the universe at whatever scale we want to. Sorry. So yeah, while it's possible, okay, further questions. While it's possible, the reason for this is already known and I have simply not stumbled upon it yet. I also find pretty interesting that in the top half of the figure 3 graph, the electron antineutrinos have a significantly larger, yeah. These are the electron antineutrinos, and these are the electron neutrinos. They have a significantly larger initial initial energy in, or initial no the initial energy, my script is wrong, even though they end up in roughly the same place as indicated by this straight line, right? I'm not sure why they have a larger initial energy. That might be some kind of spontaneous symmetry breaking thing. I might have to look into that, create an addendum or something. I don't know. Aside from that, this paper makes me want to learn about how it's possible to have densities so much larger than the density inside a given nucleus, right? Like, how do particles fall into a different sort of like packing configuration that lets more fit inside? And to touch on the previous paper a bit again, how these uh how these don't just become core gluon plasma when they're packed together that tightly. Like, it makes me want to investigate, purely as an educational thing, how neutrons and protons actually bind together at the strong force level. Since I also recently saw an article that the actual structure of protons is much more complicated than just up, up, down, because there's actually like a sea of quarks as the subject of the next paper. I think the next paper, yeah. The paper we're talking about now also mentions that the code they use to make the graphs can't work with sufficiently low temperatures to predict the crystallization of the other models with lower L values. And while I did, for a brief moment, consider trying to tinker with it, the acknowledgements did point out the code ran on the supercomputer. So suffice it to say, I will be humbly staying in my lane with this one. Also, postscript, a cool thing I found while researching this is Voronoi cells. I couldn't fit them into the whole thing. The Wikipedia page for which I have linked. Um, I came across these while trying to make sense of the concept of cells within the neutron star, which, from what I can tell, are basically mathematical constructs to help us understand how the regions close to some representative heavy nucleus within the neutron star behaves, right? And within the neutron star itself, these cells, with the black dots kind of representing the representative nucleus. No pun intended, unfortunately. Um, yeah, and around which the rest of the neutron star cell kind of forms. Um, I'm not 100% sure if I'm remembering this correctly, but I'm pretty sure the Voronoi cells also have something to do with like how treetops aren't perfectly circular. Which like everything is interconnected. That's so cool. Yeah, okay. More than halfway done. So paper 4, determination of quark-gluon quark interference within the proton, by Vladimirov, Portela, and Rodini. Yeah, this paper talks about the interstruction of hadrons and something called the Parton distribution function. Basically, as I mentioned earlier, what happens inside, say, a proton is actually much more complicated than the quote-unquote stable composition of two up quarks and one down quark that we're taught, I guess. I don't know if you were taught this. I wasn't. I learned this while, I don't know, doom scrolling on Wikipedia. Hooah. Awesome. This paper's aim is to figure out the inner structure more deeply to include quark-gluon quark interactions, as stated in the very title, by incorporating a new level of Parton distribution function into this framework. If that makes no sense to you now, that's very fair. Let's get into what all this means in more depth. So yeah, first we need to introduce some definitions. Partons are all the constituents of a hadron, a proton and neutron, basically. The quarks and the gluons. The quarks you usually think of making up, say, a proton, that those being up and down are called the valence quarks. All the other quarks whose distributions are probabilistic are called the c-quarks. Now for the Parton distribution functions, or PDFs. This paper talks about so-called twist 3 PDFs, whereas before we only had a rigorous framework behind the twist 2 PDFs, which represents the distribution of C-quarks within the proton. Twist 3 PDFs, on the other hand, represent quark-gluon-quark interactions between these C-quarks and maybe also the valence quarks. I'm not sure. As also shown by the paper's title, right? The reason for this naming convention of twist appears to be because twist 3 PDFs are also restricted by the twist 2 PDFs, which makes sense since if there's no C-quarks in a particular place, for example, then there won't be any quark-gluon interactions with those quarks. That being said, twist 1 doesn't appear to be a thing in literature, maybe because of what would be twist 1 under this framework of restricting the next PDF would actually be something completely different. Twist 4 is, however, described in literature, although it does not have a physical interpretation due to not fulfilling certain conditions on the values of the probability distribution. At the most intuitive level, this is like if, say, the sum of all probabilities doesn't add to 1, though the paper, which actually discusses the reason, is linked below. I also want to talk a little bit about the parameters considered, but before we can do that, we need to talk about semi-inclusive deep inelastic scattering, or SIDUS. It's fitting that that sounds a little bit like sadist. I'm sorry. Mom, I know you're watching those. Gosh, I should shut up. Yeah. So firstly, we need to define what deep inelastic scattering is. So while both are techniques to probe the inner structure of hadrons, protons, as discussed here by shooting high-speed leptons, such as electrons and muons at the hadrons, the difference is deep inelastic scattering like measures or takes into account only the final, say, like velocity, though there's probably more to it realistically, of the lepton being measured, while SIDUS, the final velocity of the hadron is also measured. The functions and constants themselves are tricky, however. The structure function mathematically is proportional to the integral of the Parton distribution function over the highlighted regions of figure 1. This is figure 1. We'll figure it out together, I promise. Because of this and the description provided on Wikipedia, I interpret this function to be describing all possible structures within the hadron, summed over and happening all at once, hence representing the overall structure. Whether or not that is the precise definition is beyond me, especially considering there's two small regions ignored by the integral, like these white regions. And it doesn't like appear to, and like later we'll see, like it doesn't appear to make up for that. Because like the empty region is the one with this spike right here, and the region that we're doubly integrating over is like this region right here. I don't know how it works, okay? Cut me some slack. Yeah. Yeah, I don't know. Feels scary. Yeah. Okay. However, as with the mass gap paper, I don't believe it to be paramount to understand the precise physical significance, especially when the thing we're trying to get is so abstract. If we can convince ourselves the things we're measuring and trying to get are related mathematically, again, I encourage you to stare at the paper yourself blankly for a couple hours to feel what I just absolutely I'm sorry. I just like grabbed my microphone. Um, yeah, if we can convince ourselves it's related mathematically, then we can do anything. The second parameter discussed is the moment, which is instead the integral over the whole hexagon in figure 1. Because the paper says this value is usually very small, I think of this quantity, I think this quantity represents which interactions are most likely to occur. Like it's almost a weighted average, I would say. Yeah. Onto the two asymmetry parameters, the single spin and double spin asymmetries from a different paper, also linked. Actually, two different papers, also linked. We can see the former is defined as a difference in cross-section when the helicity or handedness of the lepton, which we're shooting at the hadron, is flipped. Do with that what you will, honestly. It's like if the spin is flipped or if the direction we're shooting at it is flipped without flipping the spin, like it's handedness, okay? CP violation, I don't know. Yeah, as for the double spin asymmetry, I wasn't exactly able to make sense of it, but perhaps you would with the aid of the diagram, which seems prevalent in discussion of spin asymmetry. Let me try to pull up the diagrams. I don't think I actually have it in my slides. Okay, hold on. Hold on. I'm an idiot. Oh my God. I didn't pause recording. I paused the screen share. I'll have to edit that out. Hold on, let me unpause the recording. Oop. Yeah. This is the diagram. Let's just sit with that for a sec. Yeah. In my defense, Zoom controls are really complicated. Cut me some slack. This is my first time doing this. It's a test run. Chat, it's a test run. Yeah. Okay. Maybe you'll be able to make sense of this. I don't know. But those are the parameters. So there's not as much graphs as there are diagrams in this paper, and the most important is figure 1, as mentioned earlier, and this is the domain of the twist 3 PDF we're discussing, or alternatively, the space of events which the distribution function predicts the probability of. And these events are described as interferences, basically having the distribution function describe the probability that a certain momentum partition, we'll get into what that means, will occur given a quark and a gluon state. The tricky thing I can't quite wrap my head around is I'm pretty sure there's not just like an infinite or excess supply of gluons. Instead, they come into existence to mediate core contraction. So I'm a bit confused as to whether this is maybe another constraint on the PDF. But this is most definitely just a me problem. I do not understand quantum chromodynamics, y'all. Anyways, the three coordinates that of the space represent different momentum fractions in the fields. If it makes a bit more sense, negative values correspond to a Parton absorption process, whereas positive values correspond to a Parton production process, both as stated in the paper. In the brackets are the kinds of states which interfere with each other, the so-called partonic interferences. I did not do this figure justice in my script. Oh my gosh. Who wrote this? I think I was sleep deprived, y'all. I'm so cooked. Yeah, so this is basically one quark, and this is a quark and a gluon, and these are interfering with each other in some kind of way. Hold on, let me actually pause the recording and try to like make sense of this on the fly because I did not write it down. Okay, yeah. What this appears to be to me is like this gluon gets no, probably not the gluon actually. Probably like this second quark gets produced and then hold on. Is there like a way to zoom in? I don't think so. Okay. I'm like that one tech illiterate teacher you had in middle school. Like I'm trying to figure out how the smart whiteboard works. Y'all pray for me. Yeah, I think it's like this second. Where did my mouse go? Dude, dude, dude. I'm like that one tech. Okay, yeah. It's like this quark getting produced and the gluon also getting produced, I think, while this quark gets absorbed. Don't quote me on that, please. Yeah, so this is the domain of the Parton distribution function, and it describes like all the possible absorption and production events with like various energies or like momenta, I think, with like various momenta, and the Parton distribution function describes which of these production absorption events are most likely to occur. Okay, so this hexagon then comes up in figure 2, as shown, with the overall Parton distribution function being drawn over it by taking the 2D graphs of the PDF with certain sets of parameters. At the center of this function are a bunch of vertical asymptotes, which can be interpreted as it being kind of hard to predict what will happen when there's nothing to work with and no momentum to distribute. You don't say. But that said, figure 2 is what the whole paper is about. It's a fit for the Twist 3 PDF just as promised. Cool stuff. In the appendix, there's also figure 3, which has Parton distribution functions on top of it. For the top down. Girl, you're better than this. For the top down and strange quarks, no, for the up down and strange quarks, as well as their uncertainties highlighted in gray. Okay. Right, up, down, and strange. As I said, this is also the thing I touched on in the first paper in regards to 2+1 flavor QCD, right? These are the 2 plus 1 flavors, right? Because up and down are in their own kind of little corner, and then strange is its own kind of little corner, so it's not just 3 flavor. Okay? Okay. So why this paper? Originally, I was going to do a different paper. However, I couldn't really get much out of that one. I still have linked it. However, it was just like full of numbers and there was only like 1 or 2 key concepts, and I felt like it just didn't fit the format. What drew me into this paper, however, was the fact I had absolutely no clue what a Parton was, and that was fascinating. I would consider this paper to be the most like self-indulgent one that I read for this video because it's just so cool. And QCD is kind of my favorite field. Pun kind of intended. Get it? Because quantum field theory. I'm funny. Pay attention to me. That I would personally want to work in the future. Hopefully. Crossing our fingers. So what does this change? This research opens many doors for further development of our understanding of what happens inside hadrons. It paves the way for finding further corrections to various QCD interactions within these hadrons. And this also has huge implications for nuclear physics and is a step towards answering the question of why protons and neutrons are the only stable hadrons. Just with this paper alone, we have a whole new level of dynamics and corrections to work with. From what I can tell, even if it's not like a whole order of magnitude, having these Twist 3 PDFs gives us insight into a whole new level of, like a whole like order of expansion below what we know now, and it also incorporates gluon dynamics into the mix, which whereas from what I'm getting before, we only like had the quarks being considered. Again, I feel the need to emphasize that such fits have never been described before. This is a completely new ballpark to both develop and maybe test QCD on, right? Further questions. As always, I still want to have a better grasp on some of the mathematics used in this paper, especially what the diagram I showed earlier, right, figure 1 means, since it seems interesting. As for further research questions, the paper practically serves it up to us. Further parameters which depend on Twist 3 PDFs should be considered, both with existing datasets and in further experiments. Even though I didn't highlight it, it did talk a little bit about like existing data from which it pulled this fit. Actually, what am I saying? I have the paper pulled up. I can literally just show it to y'all now. Yeah, look, it's fitting these like parameters for the Parton distribution function. Okay? Okay. And yeah, because this research is like so state of the art, there isn't really a lot I can say in terms of like a concrete direction we should go in. Like everything seems possible right now. Okay. Final paper on active matter. A complex topological phase in C-spin active matter. Yay, by Alessandro Schiré. I hope I pronounced that right. So this paper is about active matter whose constituents move around in complicated patterns which exhibit emergent behavior. Specifically, the author comes up with a new type of this active matter called C-spin or complementary spin matter. Within this type, there's 2 kinds of particles, say one which spin up and one which spin down, or clockwise and counterclockwise. This paper analyzes which kinds of configurations emerge from various parameters. Specifically, it focuses on the difference in the spins. I should probably show this. Yeah. Specifically, it focuses on the difference in spins, this delta thing right here. Think of this as how quickly in opposite directions they're spinning. In the paper, this is parameterized as delta, or the circular anisotropy, or just the anisotropy. Yeah, as I said, I believe this paper is also served by the approach I took with the neutron star one, and hence I will be explaining any principles or concepts that come up as they are needed. Okay, so overall, the results are as follows. When there is no spin at all, the up and down particles just kind of stick to each other, as in figure 2, right? When delta is equal to 0. From what I can tell, this is basically analogous to how the poles of a magnet would behave, but frankly, I'm not sure if this is how it would work with, say, like differently polarized electrons in some kind of condensed matter material, and I'd wager not. When the spin difference parameter anisotropy is between 0 and 0.5, the arrows still roughly stick to each other. However, an angle forms between them, which depends on this parameter. However, I'm not very knowledgeable on the Kuramoto model, on which much of the maths of this paper seems to be based off of, and I can't make sense of the physical interpretation of this angle, though I would presume it's symmetric in the sense that the angle being pi plus arcsine 2 delta instead of pi minus arcsine 2 delta would make just as much sense in the theory, although to some extent, figure 5 makes me doubt this, as the angles play a role in the direction of the spin of the motion, as you can, of the spin of the spin of the, play a role in the direction of the motion of the dipoles. Thank you. C-dipoles, as the paper calls them. It's a little bit like how like everything quantum legally has to start with a Q. Everything in this paper legally has to start with a C. Awesome stuff. I generally who let physicists be in charge of naming things? Also, absolutely no shade, by the way. I just find this endearing. Okay, like sue me. Don't. I'm broke. Um, yeah. So perhaps when the sign is switched, it'd be like switching the physical interpretation of the up and down spins. Like as you can see, I made a little change to the diagram because I was screenshotting this from my own personal annotated version of the paper, right? Like, but like if you rotate this around, I feel like it'll look like this with hold on. Right, this is plus instead of minus. I feel like if you like rotated this to here, then the red arrow would be in place of the like old blue arrow. So I feel like it'd just be the physical interpretation being switched. Don't quote me on that, please. Yeah, okay. And beyond this, a total instability regime occurs and the poles no longer stick to each other. And as I mentioned just now, figure 5 is interesting. It shows the various emergent patterns which can show up depending on the values of delta, the anisotropy parameter. These are classified into vortices and anti-vortices. In the former, the dipoles will go around the center clockwise, while for the latter, they will go counterclockwise and both only one time, as stated in the paper. The interesting panel is D, where another smaller loop appears, and this is a little bit of foreshadowing. While the paper notes this is also a vortex type scenario, it gives us a sort of foreshadowing. Yeah, that's what I said. Yeah, when analyzing more complex dynamics which arise when the system size is greatly increased, because here we just have 80 of these little c-dipoles, and in these like seemingly solid loops, it's actually like a bunch of them packed really tightly together, as we will see later. when the resolution is increased a little bit. Okay. Yeah, so these loops form sort of like webs around which the other dipoles rotate. The paper also makes a point to discuss topological phase transitions, most of which I have summarized above with the vortices is type 2 topological phase. The type 1 is simply when nothing is moving and all the dipoles are sticking to each other, as in the first panel of figure 2, right here. Whereas type 3 is total chaos. Yay. The transitions between these phases are summarized in figure 6, whereas type 3, in figure 6, which shows the time average kinetic energy against the anisotropy parameter. Of course, many simulations were ran to ensure the results weren't skewed by random chance, which is why the error bars are present. Um, why time average kinetic energy is chosen should be obvious. Not only is it a measure of movement, but it also seems to define a sort of temperature, oddly, for this paper. Um, Even though that's not outright mentioned. What else do we have? Okay, final questions. Why this paper? I just wanted to have a paper on a field that's only tangentially related to what I think of as physics while still being comprehensible to me. And in my defense, this was under the physics section of arXiv, okay? I think in general, it's healthy intellectually to explore various fields, not only when you're trying to figure out what you want to do in life, but also to have a greater perspective on the kinds of things you may be able to do after you've achieved like this sort of dream, right? Dream job. Also the graphs are cool. I know I say this about every paper, but this one has moving graphs in the supplementary material. Let's watch one of them. I'm bored. Let's watch one of them. Same as Dreamed Up by the Utterly Deranged, honestly. Also, like this graph exists. Let's read a little bit, honestly. Um, By exploring different system sizes ranging from N80 to N1000, I have observed that the values of delta required to obtain type 2 solutions decrease as the system size N increases, right? Because they tend quicker to chaos. I think that makes sense. To highlight the transition between the stability region of type 1 and the bistable region containing both type 1 and 2, I have performed extensive numerical simulations across the N-delta parameter plane. The result is reported in figure 8, where white dots indicate the presence of a type 1 uniform solution, and the black dots denote the emergence of type 2 vortex complexes. Okay, that's what this is about. I thought it was kind of like a game of life thing, honestly, or like Conway's game of life kind of thing at the start, but it's not, unfortunately. Okay. The analysis reveals that as n increases, the transition value of delta, previously termed delta low, decreases following the empirical scaling relationship of this, where a is the fitting parameter. Okay. Blah, blah, blah. Yeah, this graph is pretty cool. It's like, so it's like, there's like this boundary where the further you go into this boundary, the quicker these kinds of things arise. And you know what I'm actually interested to compare? The little D diagram in figure 5, that was 0.22 with 80. 0.22 with 80. Hey, that's pretty neat. It's like the square, right? Right, I think so. So it's like around this square, and I wonder if it has like any significance with the fact that it had like that kind of daughter loop. Again, like this is genuinely interesting to me. Let's watch one of them. Okay, larger systems. Look. Oh yeah, hold on. Yeah, I almost missed this. Yeah, as you can see, like these complicated noodle-like webs, they're actually made up of these small little c-dipoles. They're just like packed so close together that you can't see that in the diagrams I included in the presentation. Okay. There's blatant favoritism in this video. I am blatantly favoring this paper, and that's okay. Who cares? I'd make a really good scientist, honestly. Okay, hold on. There are links. I sure hope these still work. Ooh, Google Drive. Hold on, let me set that up. Let me set that up real quick. And hello, computer. Okay. It appears to be working. Look, they're spinning. They're spinning. That's so cool. What? Look, it's like kind of figure eight thingy. Wow. Oh yeah, because like oh yeah, the paper like mentioned earlier that it was like kind of like a long exposure photograph, which is I think partly the reason that they seemed so tightly packed together. Okay, yeah. I should have totally included these in the presentation. What? These are so cool. Look. Wait, what is spinning? And these would also like move around, kinda, right? They're not moving. Wow, okay. Nice. Highly intricate compartmentalized network. Sure. Wow. Look, they're like flipping. Flipping depending on like what stage this is in. Okay, so I guess they're not moving. Like the rest of these. That's pretty cool. Yeah, I guess there are in like some kind of like stable configuration, like all of these. Almost like a type 1 thingy. Wow, that's so cool. What? I wonder how this was made. Okay, anyways, getting back. Further quest, what was I doing? Yeah, yeah, what was I doing? Yeah, also the graphs are cool. Yeah, cool. Yeah, so as for the subject matter itself, so what does this change? As for the subject matter itself, to me, emergent behavior is intrinsically interesting on a philosophical level because so much of what we see in our daily life is emergent, hence why I chose this paper, even though like it's not going to be describing society or anything, I guess. Okay, further questions. As the abstract states, this research is ooh, what? Huh. Okay. Oh, right. Okay, that makes sense. As the abstract states, this research is applicable in understanding the morphogenesis of living systems. Whatever that means. Probably something with birds. I mean, have you seen birds? Exactly. Okay, but in actuality, it's like um the way that living things arrange themselves and living things form shapes, specifically, I think in the context of tissues. Okay. And in general, it seems like the field of active matter is quite up and coming with different models being developed and refined. And I'm sure this research will be a stepping stone towards developing some bigger model that will find great applications in maybe living systems, computer science, or even some kind of medical nanotech. I don't know. Absolutely no basis for that, by the way. Simply what I first thought of when I read the abstract. Um, and yeah, because active matter appears to be a very new field of research, I can't really think of any concrete further research questions off the top of my head. Of course, I do want to learn more about the mathematics behind this. And there's definitely countless ways to further develop this framework, such as maybe adding more dimensions or more combinations of locking between various spin directions, for example. Also, while I have no understanding of chaos theory whatsoever, even though I am going through a textbook that talks about that eventually, okay? Be employed era soon. It will be interesting to try to analyze exactly how this system descends into disorder when the anisotropy parameter is increased. We didn't have any moving graphs for that, unfortunately, but maybe I can get my hands on the code. Trust. Okay, so, and matter for the video. What I learned from the process is I should probably read the papers during the month which they were published, okay? Yeah, so that I wouldn't be releasing this on the 18th instead of the 1st, or like the first week of December as planned. But you know what? We ball. This was like very much a test run kind of video just to see what I'd be able to do, how much I'd be able to figure out with my limited like foundations, I would say. So in the future, I think these are going to start being a little bit more coherent, hopefully. Yeah, awesome. But I do still want to do these kinds of videos, and I kind of foreshadow those, but I might like do paper reading videos where I go through a paper like line by line, like I sort of did with this one. That is definitely something I want to do, but once again, like there's like so much nitty-gritty in all of these papers that I completely glossed over for sake of summarization. And also for sake of, you know, not torturing myself with the mathematics because I mean calculus is fun actually. Like I would say calculus is like torture hell, but it's fun actually. So I feel my point slightly withering away here. Um, yeah. Lots of raps we've been getting this year, right? Like Spotify Wrapped, mm, YouTube Music Wrapped. I'm sorry, I'm a music girly through and through. I'm sorry. But yeah, a lot of like Wrapped. So we've been getting a lot of memes about the Wrapped. We've been getting a lot of notifications I've been getting from like Google. Since when does Google send you notifications? Honestly, like can we talk about that? Um about like stuff being published in science news outlets about like the coolest discoveries of 2025 or whatever. And that is like a hype train I want to jump on, honestly. Like yeah, I want to do that before 2026 because this year seems to be like the prime target. 100 years of quantum mechanics this year. We really locked in this year for real. Like I locked in. I started doing like APs or like studying for APs. I started like um doing more advanced physics. I am planning a video on special relativity or like a module on special relativity following Goldstein and the other textbook that I am also doing. Probably going to be next year, considering I'm going to be rushing really hard for physics wrapped. But yeah, a lot of cool stuff. In researching for this video, I also found a cool paper about neutrinos and potential new neutrino flavors that were actually specifically that they were confirmed to like one additional neutrino flavor was confirmed to not be able to solve physics. Um, it was at the Fermilab thing with the microboons. So yeah, I definitely want to cover that. The reason I was searching that up is actually because I wanted to have a module or like a section in this video about like not necessarily debunking, but providing more accurate context to a physics clickbait title thingy in one of the news places for science. And I totally understand that like physics is one of the most low stakes fields you can have. Like it is so far removed from anything normal people would care about. But unfortunately, I don't know biology, so I can't cover a medicine like clickbait title. I'm sorry, like I'm doing what I can over here. But yeah, I was basically searching up like physics news and then clicking on the news tab to get like clickbait titles because I wasn't getting anything on my phone. And I just like came across this microboom paper that was published like 3 days ago at the time, and I was like, wow, faith in humanity restored. Can I just say that? Like, yeah, okay. Um, cool. Cool. Enough yapping. Absolutely yap y'all's ears off. I'm sorry. Nobody's gonna watch this, gonna be kidding. But please do watch this. If you watched till here, you get a cookie. Okay. Um, you get to look at, do you get to look at this cat plush I got? It's being blurred. It's being blurred by the background. Oh my gosh. Can I just like, put my hand in front of it? But yeah, okay, fine. If you made it this far, you get to see him. And that's it. Thank you for sticking around. Hope you found this at least like somewhat enjoyable or educational. Hope you like my voice. And see you next time. All right, thank you. Bye.